So when I introduced the concept of power factor in Monday's class, we talked about how it is a measure of the efficiency of transmission, where a power factor of 1 means that we are absorbing power at 100% efficiency, and a power factor of -1 means that we are supplying power at 100% efficiency, or our load is supplying power at 100% efficiency. Large industrial consumers like manufacturing plants often operate at a power factor that is less than 1, meaning that there is some amount of inefficiency in the distribution. And this inefficiency arises from the fact that loads like induction motors and things operate as temporary energy storage elements. So effectively, the electric utility pays some amount of money, either by buying coal or supplying the infrastructure to transmit power to the utility, and then some small portion of that gets sent back to the utility. So there's an inefficiency there, okay? So if an industrial consumer operates at too low of a power factor, they are effectively wasting the utility's money and they receive a fine. So to combat these fines, a technique called power factor correction has been developed. So I'm going to describe that process to you guys. So let's consider a generic inductive loads power triangle. So this is our imaginary axis. This is our real axis. And let's say that this load is drawing power, complex power S, like so. I'm going to call this S old because this is what the complex power looks like prior to power factor correction. The real part of S old is P old, the average power before power factor correction. And the imaginary part of S old is Q old, the reactive power prior to power factor correction. And finally, the angle formed between S old and the real axis is going to be theta old, the power factor angle before power factor correction. So if we want our load here to operate at a better power factor, or a power factor that is closer to 1, do we want that angle theta to become larger or smaller? Smaller, because cosine of 0 is 1. So the closer that we can get that angle to 0 degrees, the closer and closer we will be to operating at unity power factor or 100% efficiency, okay? So in order to increase our power factor, we have to, in some way, shape, or form, reduce that angle. So there are 2 ways that we can do it. One of them is wildly stupid. So let's talk about that one first, okay? So if I increase the resistance of my load, okay? So let's do this in, oops, pink, right? So let's say if I increase the resistance of my load while keeping the reactance of my load the same, this pink line would represent S new. The projection onto the real axis would be P new, and the projection onto the imaginary axis would still be Q old. Does that lower my power factor angle? Yes, okay. Now let's talk about why this is wildly stupid, okay? So the average power is what we as consumers pay for, and the apparent power is what the industrial customer provides, or the industrial supply provides. So if we used this method of power factor correction, we would be increasing our utility bill to offset a fine. Doesn't make a whole heck of a lot of sense. So while mathematically it gets us the results that we want, practically it's the dumbest thing that we could do, okay? Because we would effectively say, in order to avoid this ongoing fine, we will pay more ongoing money. It's just the fine in a different form, okay? So increasing power factor by adding resistance is very, very dumb. So we're going to erase this because of how utterly stupid it is in practice to do it. So if increasing P is a bad idea, what about decreasing Q? So if we can get our load to operate at a lower Q value, let's say here, while maintaining the same average power, well, that line isn't where I want it to go. Like so. So if this is S nu, we can see that theta nu is indeed smaller. So our power factor has been increased. We are not increasing the amount of average power that is consumed by our load in any way, shape, or form. So we are not running up our utility bill. Effectively, we have a one-time cost of putting something in our system to make Q smaller, and then we're good to go. So what do you think we should use to make Q smaller? So recall from the end of Monday's meeting that the complex power absorbed by an inductor was given by, let's see, I'll have to think about this because I don't have it written down in front of me. Let's see, so it's going to be the magnitude of the voltage, so V effective squared divided by negative J omega L. So that's going to look, the negative J is going to come out as positive J over here. And this is also the same as J omega L times I effective squared. So inductors absorb reactive power. Capacitors, this is going to look like negative J omega C times V effective squared, or negative J I effective squared over omega C. And resistors, behave like this. So if our goal is to make Q smaller, which element should we use? You have a 33% chance of getting it right just by blindly guessing. A capacitor. So you got it right on the first try. Did you blindly guess, or do you have a reason behind that guess? Okay. All right, well, that's one way to do it. So our in-class assignment problems both mention doing power factor correction by including a capacitor. So the reason why we would use a capacitor for power factor correction is because we want to reduce Q, the imaginary part of our complex power. And if we look at our capacitor equation here, in both cases, whether we're dealing with an effective voltage or an effective current, we're providing a negative reactive power, right? So this difference between S old and S new is going to be S cap. So effectively, if we want to hit a specific power factor, we now graphically have a relationship to figure out what size capacitor we would need to do that. So now let's go through things mathematically. All right. So S old, the complex power prior to power factor correction, is P old plus JQ old, which is the same as the magnitude of S old with an angle of theta old. S new will be P old plus JQ new, or in polar form, the magnitude of S new, angle theta new, and the amount of complex power that our capacitor needs to provide is simply the difference. S new minus S old. So in rectangular form, this is going to look like P old plus JQ new minus P old plus JQ old. And we can see that the real parts completely cancel each other out, which should be expected here because our capacitor is only capable of providing either reactive power. So we're going to have J Q new minus Q old, or J times Q cap. Okay. So I want to point out something here. This quantity Q cap will always be negative because we are trying to reduce our angle here. Okay, so we're trying to make effectively the magnitude of our complex power small. We can equate JQ cap to either this expression for the complex power provided by a capacitor or this expression. 99.999% of the time we use the voltage relationship because we transmit power using voltages. We don't use current sources or anything like that, okay? So if I set S cap equal to S cap, I can then solve for C. And what I will find is that C, the capacitor needed to increase my power factor, is equal to negative Q cap. So this is the amount of reactive power that our capacitor needs to supply, divided by omega times V effective squared. So this is if we know how we're correcting power factor, if our complex power that we need is known. And we can also write this as P old tangent of theta old minus tangent of theta new divided by omega times V effective squared, which is useful if we know what our current power factor is and what our target power factor is, because those are related to the angles theta new and theta old. Okay. So let's look at your in-class assignment. This is number 24, right? So when connected to a 120 volts RMS 60 hertz power line, a load absorbs 4 kilowatts at a power factor of 0.8 lagging. So I'm going to draw a picture of what this looks like. So we have a voltage source, and we know that V effective is equal to 120 volts RMS at a frequency of 60 hertz. We do not know what the phase angle is, just to be clear. And then we have a load over here that is absorbing 4 kW at a power factor of 0.8 lagging. Okay. We do not know what our load is, nor do we particularly care. I could say based on the power factor, the fact that it's lagging, it is some sort of inductive load, but beyond that, I don't really know. Okay. Our power factor correction scheme is literally throw some capacitance C in parallel with our load to improve its power factor. Okay. So if we want to apply the equation that we just developed, we need to know the following pieces of information. We need to know P old. We need to know theta old. We need to know theta new. We need to know our angular frequency omega, and we need to know our effective voltage. If we can get those 5 pieces of information, we can just plug that in to our equation and call it a day. So which of these pieces of information are we given? So V effective, we were told, is 120 volts RMS. Okay. What else were we given in the problem statement? So the frequency was given as 60 hertz. So omega is just 2 pi f, or 120 pi radians per second. Okay. What else were we given? P old is 4 kilowatts. So we weren't given theta old and theta new specifically, but we were given PF old and PF new, our power factors, which are related to theta old and theta new. So theta old should be the inverse cosine of 0.8. If we recall that power factor, by definition, is cosine of theta s, we can figure out the angle if we know the power factor. So the inverse cosine of 0.8 is, I think, 36.87 degrees. Let me get a calculator out and double check that. That's right. Okay. I wasn't able to do that in my head, just to be very clear. This is a very common number that shows up, so I just happen to remember it. So not some kind of weird inverse trig function savant. The inverse cosine of 0.95, I do not have remembered, so somebody please tell me what that is. 18.19 degrees. All right. And so now we have everything that we would possibly need to calculate our power factor. So since I left all of my calculators on my desk yet again, please calculate this and tell me if it matches the result that we're looking for, where our equation is C is equal to P old tangent theta old minus theta new over omega times V effective squared. Oops, sorry. There should be a tangent theta nu here. It's not just theta nu by itself. Andrew, are you nodding your head in affirmation that my answer is correct? Good. So 310.439 microfarads is the answer that I have written here. I have one student that confirms that I was correct when I wrote this problem, I don't know, 4 years ago or whatever. Anybody else get this result? Other people nodding their heads. Great. So let's take this one step further if we can. I want to ask you guys a question, and it is an important question that I have not yet asked. So right here, our target power factor is 0.95 lagging. What if our target power factor were 0.95 leading? How would that change our analysis? Or would it change our analysis? Let's start there. So somebody says they're sure. Yeah, Daniel. That is exactly correct. Okay. So whenever we have a leading power factor, we know that our power factor angle is supposed to be negative. So if we had a leading power factor, we would have a negative sign in front of our inverse cosine operation, forcing this angle to be negative, which would in turn propagate down further, and we'd find out that we'd effectively need a larger capacitor to facilitate this. Okay. There's not any real practical reason why we would ever want to push our power factor from lagging into leading. That being said, when we do our power factor correction lab, that is exactly what you guys are going to do. You're going to start by having a particular load. You're going to place a capacitor in parallel with that load to improve its power factor to almost unity. And then when you put a second capacitor in parallel, it pushes it further, so much so that the current starts to lead the voltage, thereby giving us a leading power factor. Let's look at problem 2 real quick here. Okay. So I'm going to draw our circuit again. In this case, we have a V effective is equal to 230 volts RMS at a frequency of 50 hertz. source connected to a motor. And our motor has an impedance of 25 plus J10 ohms. We are performing power factor correction, meaning that we are going to place some capacitor in parallel, like so. And we want our power factor PF new to be 1.0. So this problem is incredibly similar to our last problem, but the information is presented in a vastly different way, but we can effectively work it out the exact same way, okay? So we're still going to need to know theta old, theta new, omega, and V effective. We were obviously given V effective 230 volts RMS. We were given enough information to find omega. It's always 2 pi f, so this is going to be 100 pi radians per second. We were given enough information to figure out theta nu. Since the power factor is unity, that means theta nu must be 0 degrees. Because if we want the inverse cosine of 1 is 0. I'll write that down more specifically. Inverse cosine of 1 is 0 degrees. So the only things that we need to figure out here are P old and theta old. Anybody have any thoughts on how we might do that? We need to find the power absorbed by the motor. Sure. So from our alternative relationships that we developed at the end of Monday's class, S for the motor could be written as V effective squared divided by Z motor conjugate, right? Because we want the RMS voltage drop across the motor, which is V effective squared, and then we are dividing by the conjugate of the impedance, because we are utilizing the relationship S is equal to V times I conjugate, where I conjugate can be written as V over Z conjugate, which is the same as V conjugate V over Z conjugate, where V conjugate V is the magnitude squared. So anyway, just rederiving the equation that we're using here. So we have all of the pieces of information that we would possibly need. So this is going to look like 230 volts RMS quantity squared. How do I do the conjugate of a rectangular form complex number? What was that? Change the sign on the imaginary part. So if it was 25 plus J10, the conjugate is 25 minus J10. So somebody please tell me what the result of this calculation is in both the polar form and rectangular form. One 1.964 angle 21, 8 degrees, and this would be kilovolt amperes because we're dealing with complex power. All right, so convert that. Actually, did anybody else get that? Okay, Daniel, you have the rectangular form? Wait, so 1.4. Okay, so I had a decimal place in there that was going to mess things up because one would have been in kilowatts and the other one would have been in bars. So I'm just making it to where it's all in the same scale. VA. Okay, so what's P old? I disagree. 1.964 kilovolt amperes is the apparent power before power factor correction. I am looking for the average power before power factor correction. It's written up there. You just got to tell me which number it is. 1824. So 1.824 kilowatts is P old, because the real part of the complex power is the average power. What is theta old? Yes, literally the only angle I have written anywhere. 21.8 degrees, because the angle of the polar form is the power factor angle. Okay. And now we have enough information to plug directly into our calculator and determine C, which will come out to be this number. Okay. So two different styles of power factor correction problems. Just wanted to show you those. So I am going to not really waste you guys' time, but we're going to work one more problem, and it's from your web work. And it is probably one of the hardest problems that whoever wrote them tried to give you guys. If we approach it in this form, we should be able to knock it out in about 10 minutes. One time I watched another professor try to do it and it took him 45 and I just giggled the entire time. It's not that hard. And I'm a conceited jerk. So let me pull up web work here. So I believe this is homework set 24, and I believe it is the last problem. Let me double check to make sure. Yeah, this is it. All right, so this is the circuit that we are going to be analyzing here in order to determine the value of the capacitor that gives us a power factor of 0.92 lag. Okay, so I'm going to write down the circuit and the critical pieces of information. So we have some voltage source. We have some capacitor C that we're trying to calculate. That's our power factor correction capacitor. We have some resistance R. And then we have some load that I'm going to designate as an impedance ZL. Let's go back over here. So let's see. The load is operating at 14.8 kVA. with a power factor of 0.53 lagging. R is 5.4 ohms, so I'm going to write this up here. Nope, just ohms. We know the current flowing through the load, but we only know the magnitude of the current. So the magnitude of IL is given as 23 amps RMS. We do not have the phase angle, just to be very clear here. We are not given a value for VS. And let's see, our power factor nu is 0.92 lagging. And our source is operating at a frequency of 60 hertz. Okay. So let's write down once again our needed pieces of information. Okay. So we're going to need P old. We're going to need theta old. We are going to need theta nu. We are going to need omega. And we are going to need the magnitude of the voltage drop across the capacitor. Okay. So with the information that's presented to us, the only thing that we can glean here easily are omega, because we know F, and theta nu. Okay. So omega is going to be 2 pi F, or 120 pi radians per second. Theta nu is going to be the inverse cosine of 0.92, which I can't do in my head, so somebody please tell me what that is going to be. 23.07 degrees. Thank you. You might think we have theta old as well, because we have the power factor at which the load operates. The problem here is that the capacitor isn't directly in parallel with the load. There's that resistor in the way. So we need to actually find the total complex power of the resistor in series with our load in order to figure out what theta old is. Okay. So let's work on that. How do you think we might go about doing that? So, finding the impedance ZL, that is going to be problematic because we only know the magnitude. No, that's not true. Yeah, we could find the impedance ZL. Sure, let's go that route. So how would we go about finding the impedance ZL? All right, so the complex power absorbed by our load is going to be 14.8 angle inverse cosine of 0.53 EVA. That succinctly putting what you were doing there? How do you mean? In a good way or a bad way? No, this is a very good way. Yeah. Yeah. So what's the inverse cosine of 0.53? 58 exactly? Okay. So 14.8 angle 57.99 degrees kilovolt amperes. Okay. The impedance of our, I'm going to write load here because I don't want you guys to confuse it with the complex power absorbed by an inductor. From our alternative relationships, we know that this should be I effective squared, so the magnitude of our effective current times our load impedance. So that's just using our alternative relationships, right? So if S is equal to V RMS phasor times I RMS phasor conjugate, and Ohm's law tells us that V RMS phasor is I times Z, then we have I RMS phasor times I conjugate RMS phasor times Z, or the magnitude of the current squared times Z. We know S load, we know I effective, we can now solve for Z. Is that not the method you were intending to use? So Z load here is equal to S load divided by I effective squared, which would be 14.8 angle 57.99 degrees kilovolt amps divided by 23 amps RMS squared. Just to be clear here, I would call this 14.8 times 10 to the 3 when you put it in your calculator, so that we get an answer that is in ohms, not kilo ohms or something weird like that for our impedance. So somebody please tell me what's what. In, let's say, rectangular form. And that's in ohms. So Zachary, may I borrow your calculator? I'm sorry. And Travis, I apologize for my incredulousness here. I just want to double check things. Yep. Okay. Thank you. That just seemed small to me. That's all it was. All right. So that's the impedance of our load. So what is the total impedance in parallel with our capacitor? Well, it's just going to be Z load plus 5.4 ohms, right? So I'm going to call this Z load prime. Is just going to be the Z load plus effectively the resistance of our wire, which was given as 5.4 ohms, is going to be 19.83 plus J 23.72. Oh. Okay. So from this, yes, 5.4, you're right, thank you. 20.22. Added 5 ohms to it instead of 5.4. Thank you for that. All right, so how do we calculate the total complex power absorbed by our load, our composite load here prior to power factor correction? The answer is already written here. Why can't we just use this equation again, but including the resistance? Right, we have all of the pieces of information for it. So that's going to be 23 amps RMS squared times 20.22 plus J 23.72 ohms. Which comes out to be 10.701 or 702, I'm rounding correctly, plus J 12.550 kVA. In rectangular form, and 16.493 angle 49.545 degrees kVA in polar code. So what's P old and what's theta old? That's correct. So P old is 10.701 kilowatts. The real part of S theta old is this 49.545 degrees. So that leaves us with how do we find the effective? We don't know what our source is supplying. We don't know the phase angle at which our current is flowing through our composite load on the right-hand side. Anybody have any thoughts? Give Jacob a credit. Okay, so our complex power so this is prior to power factor correction. Is equal to V effective, I effective, angle, theta S. Okay. So effectively, it looks like here, we could simply divide the apparent power by our current to get our effective voltage, the magnitude of our effective voltage or phasor. Okay. I don't see anything wrong with that. So let me start by saying that was not the way that I had intended to do it. What I was going to do is use S load prime must be equal to V effective squared divided by Z load prime conjugate. And that should wind up giving us the exact same result either way, I believe. So let's just verify that for the sake of argument. So if we have 16.493 divided by 23 gives us 717.086 volts RMS. Let's see. I'm sorry, that should be primed. Yeah, or conjugated, sorry. If we have S load prime, which I have as 16.493 times 10 to the 3 angle 49.545 degrees multiplied by Z load conjugate, so that would be 20.22 minus 23.72 J. No, I don't want a QR code. Square root of 500, so 514,065. 716.9, so rounding error. Yeah, okay, so this seems reasonable. All right, and that was easier to do than what I was going to do. So thank you for that. All right, so we should have all of the different pieces of information to put in here. So let's call this 717.086 volts RMS. And we now have enough to put into our calculator. So let's do it. 10.701 kilowatts. So times 10 to the 3 times the tangent of 49.545 minus the tangent of 23.07 I'm going to store that as A. And then I have omega, which is 120 pi times 717.086 quantity squared. Store that as B. And then I should just have A over B comes out to be C is equal to 41.224 microfarads. So just to be clear, I got 4.1224 times 10 to the minus 5 farads. Anybody else get something similar plugging their numbers in? Yes, Jonathan. Mm-hmm. Okay. So let's see if the web work gods have smiled on our calculator. If I can find my thing. So 41.224 microfarads. Won't say it's incorrect. Let's see if it's just rounding errors. That's a possibility. I believe wholeheartedly that our procedure here is sound. Okay. So we're just going to leave it as this. Like I said, this is one of the hardest problems in your entire homework set. But it can be boiled down to the exact same simple process steps that we have used in the other more simple problems. The big thing here is recognizing that because our load isn't directly in parallel with our capacitor, we have to take into account the fact that that resistance of the wire is going to contribute to our old power factor before we do those calculations. Another thing that we need to pay close attention to, because this is something that I've seen students do before, but you guys didn't try to do it. I have had students tell me that the magnitude of the voltage here, so let me write this down. So the magnitude of VS will be equal to the magnitude of VR plus the magnitude of V load. That is wildly untrue. The magnitude add together to make 0, because that's throwing away all of the phase angle information, which is not how complex numbers add together. So I just want to be clear about that so that when you calculate V effective, which I believe this is a perfectly reasonable way to do it, you actually get something that has some amount of meaning. Adding the magnitudes together does not work. So anyway, all right, so that's enough ranting out of me. We have 47 minutes to do the lab. Hopefully it won't take that long. It's fairly straightforward. You guys come grab your lab sheets and all that kind of jazz, and I will get out your inductors and capacitors. 1 millihenry, 10 nanofarad.